Hello everyone, welcome back to Mr. Exams Professor. So in the previous lecture, we learned about time complexity and space complexity. Now we know that every algorithm takes some time and some memory, but a question arises. Suppose two algorithms solves the same problem. How do we decide which algorithm is better? So can we simply compare the execution time? No, because different computers have different processors, different RAM capacities, and different operating systems. The same algorithm can run faster on one machine and slower on another. So computer scientists needed a standard method that works independently of the computer. So that standard method is called asymptotic notations. So let's begin. So Unit-1, asymptotic notations. So now we're going to explain about the need of it, definition, big O, big omega, big theta, order of growth, and semester questions. So let's dive into the topic. So the topic is, why do we need asymptotic notations? Why do we need asymptotic notations? So the main need of these asymptotic notations is to compare algorithms. So suppose two students write two different algorithms. So for example, let us assume algorithm 1 and algorithm 2. So algorithm 1 finishes in 2 seconds and algorithm 2 finishes in 3 seconds. So can we conclude that algorithm A is better? No, because let us assume that algorithm 1 executes 2 seconds in laptop 1 and algorithm 2 executes in 3 seconds in laptop B. So can we say that the laptop 1 might have fastest processor than laptop B, therefore measuring time in seconds is not reliable. So instead we compare how algorithm grows when the input size increases. That is why we use this asymptotic notations. So main need of asymptotic notations is machine independent, programming language independent, for comparing algorithms, to prediction of performance. Prediction or predict performance. So these 4 points are enough if you have given a 2 marks question, or you can elaborately write if there is another big question given. So I can say this is the marks area. Do note and do read this. This is very important for examination point of view. So officially, let us dive into the definition of an asymptotic notation. So the definition of of asymptotic notations. So asymptotic notation Asymptotic notation is a mathematical notation used to describe the growth rate of an algorithm. The growth rate of an algorithm as the input size becomes very large. This is important. As the input size become very large. So so you have to memorize this definition. This is the whole definition of this asymptotic notation. So let's understand it. The word growth means as the number of input increases, how much does the algorithm execution time increases. So here the growth is now as the number of inputs increases, how much does algorithms execution means the algorithms execution time increases. Yeah, that's all. This is the definition. So do memorize this. This is the marks area too. So now coming to the input size. So what is an input size? Here n means input size. Suppose let us assume that there are 10 students. Suppose assume there are 10 students. So n is equals to 10. Assume 100 students. N is equals to 100. Assume 1000 students. N equals to 1000. So as n increases, the algorithm's behavior changes. The algorithm's behavior changes. That is why we study this. Hope you understand. So now I'm going to explain about what does n infinity mean. One of the most important topic. What does n tends to infinity mean? N tends to infinity means very large input. So n tends to infinity mean very large input. So infinity does not mean we will actually have an infinite data. It simply means like imagine the input becomes extremely large. For example, 10 lakh records, 1 crore records, 100 records, etc. So then we study how the algorithms behaves. So now I'm going to explain about the big O. Big O, worst case upper bound. Worst case upper bound. Students, first let us understand about the word upper bound here. Upper bound. Upper bound means maximum. Bound means limit. Yeah, upper means maximum. Bound means limit. Therefore upper bound means maximum possible limit. Maximum possible limit. Maximum possible limit. So this is it. So for example, if I'm going to say about a real life example, suppose you have traveled from home to college. Normally it takes 30 minutes, but due to heavy traffic, rain, road work, the journey may take 50 minutes or more than 50 minutes. So let us assume that 50 minutes is the maximum expected time. So that maximum limit is called the upper bound. Similarly, big O tells us the maximum time an algorithm may take. So I'm going to write here for just to memorize it. Big O tells us the maximum time an algorithm may take. So do refer this. This is the important topic for the semester examination point of view. So here big O is the worst case upper bound. Do remember this in sequence. Note it. To remember in sequence. So now let us go to big omega. Big omega is the best case lower bound. So here lower means minimum, bound means limit. As I have explained about the bound in the previous one, big O. So lower bound means minimum possible limit. Lower bound means minimum possible limit. Minimum possible limit it is. Yeah. So a real life example is like if suppose if there is no traffic, empty roads, green signals. Now your journey takes only like 15 to 20 minutes. So you can reach in less than 15 or 10 minutes. No, that is your minimum possible time. That minimum limit is called lower bound. Similarly, big omega tells us the minimum time an algorithm requires. Means big omega tells us the minimum time an algorithm, treat it as an algorithm requires. So similarly, big omega is best case lower bound. Do remember this in sequence also, just like big O. To remember this in sequence, as I have explained about the big O earlier. So I have to remember this big omega also in the sequence. So now coming to the topic, big theta. So big theta is time bound, tight bound. Tight here, tight means close or exactly fitting. Students do see this. Tight mean like close, or you can say exactly fitting. Yeah, exactly fitting. Means a tight bound tells us that the algorithm's growth is bounded from both above and below by the same order. Yeah, I'll write it. A tight bound tells us that the algorithm's growth is bounded from both above and below by the same order. This is the type one. For exam purposes, you can remember as I write. He says yes. This is the big theta. So I'm writing this for exam purposes. So for exam purposes, do remember like what I have written now, what I have right now. So big O, big omega, big theta. Big O is maximum limit. Maximum limit. So what is maximum limit? Upper bound. Upper bound it is. Big omega means minimum. Minimum limit means lower bound. Big theta means exact growth order. Here tight bound. Do remember these are very important for semester examination point of view. Marks area. So to read the previous topics I have given and I have explained and come here. Suppose I'm going to explain now a real life example. Suppose your daily commute usually takes around 35 minutes. Some days it is a little faster or some days a little slower, but in general it stays around that value. That typical growth is what big theta captures. So big theta catches it. So now I'm going to explain why do we ignore constants. Why do we ignore constants? So 5n, 10n, 100n. Are these different? So I'm asking you students a question. Are these different? Yes, they're different. Suppose n is equals to like n is equals to like what I'm going to write here. N is equals to 10 lakhs. Here 5 and 10 and 100 and all here increases in a linear manner. All increases in linear manner. The pattern growth remains the same. Hope you observe that. Therefore, constants are ignored. So this is the reason constants are ignored. The pattern growth. The pattern growth remains the same. So constants are ignored. So 5n of n, 10n of n, 100n of n. Why? No, I'm going to explain now about why do we ignore lower order terms. Why do we ignore lower order terms? So here n square plus n is O of n square, means n square plus 10n plus 50. That means O of n square. I'm going to explain now. So when n becomes very large, when n becomes very large, n square grows faster, much faster than n or any constant. So the highest order term dominates the growth. Highest order term dominates the growth. Therefore, we ignore smaller terms. So now, order of growth. Best O of 1, O of log n, O of n, O of n log n, O of n square, O of n cube, O of 2 power n, O of n factorial. Worst. Don't worry, I'm going to explain here very keenly. Don't worry. Here O of 1, the constant time. For example, we can say like accessing the array. Accessing array of as we have to give them accessing array of 5. O log n means binary search. O of n, linear search. O of n log n, yeah, sorting like merge sort, heap sort. That's it. So this is bubble sort. O of n square is a triple nested loops. Yeah, triple nested loops. O of 2 power n is generating subsets. O of n power is it is the brute force traveling salesperson. Yes, salesperson. So do see this, to observe this. This is one of the most important thing to do. So as a summary, I'm going to write a comparison table. Equivalence comparison table. So here notation case meaning. Big O is the worst case, upper bound. Here big omega is the best case. lower bound, big theta, tight bound, exact growth order. This table is extremely important for semester examinations. So it is the marks area. So I'm going to give you some of the previous semester questions, like previous semester topics, questions from the topics. So do see this. Number 1, define asymptotic notation. So number 2, explain big O, big omega, and big theta. Differentiate omega, O, omega, and theta. So why are constants ignored? Next question, why are constants ignored? Another, why are lower order terms ignored? Okay, next, arrange the order of growth. So these are some of the most important PVQs, as well as it is also going to be repeated in the examination cycles also. If you understand today's lecture, you can confidently answer these all questions. These are very important. So final revision. Today's summary. Need of asymptotic notations. Need of asymptotic notations. The definition. Input size. Explained about big O, big omega, and big theta. Upper bound, lower bound, tight bound. We also explained about like ignoring constants. Yes, ignoring constants, ignoring lower order terms, ignoring lower order terms, order of growth, and I have explained about some PVQs are important questions. PVQs not are important, yeah, important questions. Do see these questions. Those are very important. So we completed the theory of asymptotic notations. This topic is the foundation for understanding sorting algorithms like AVL trees, divide and conquer, greedy algorithms, and dynamic programming. So in the next lecture, we will begin AVL trees, why they were introduced, what a balance factor is, and why an AVL tree only allows balance factors of -1, 0, and +1. If this lecture helped you, like the video, share it with your classmates, and subscribe to Mr. Exams Professor for the complete ADA course. Thank you, and I'll see you in the next lecture. Bye, guys.